Hi, today I'm going to talk about capacitor leakage testing. There are a lot of videos on YouTube where people have built dedicated boxes to measure capacitor leakage using an internal supply that is using some kind of a DC boosted supply using some multiplier type circuit and built-in ammeter, either analog one or digital. But I thought I would go a different route because I do have these high voltage supply and sensitive meters, and I didn't want to build a dedicated box just for that purpose. So and since for different applications you would need different ammeter sensitivities, I thought I would just build a more general purpose type of jig where I could plug in any ammeter or any supply that I wanted to use. So for very low voltage caps or large electrolytics, you can use most typical up to around 50 volts or so. You can use a dedicated bench supply, normal supply that you have lying around, and even you can use a multimeter here for leakages in the microamp or milliamps. So the basic circuit is really here. I have in this case a supply that is connected on this side, and this is meant to go up to 500 volts or so. I have a main switch here which once powered on, powers on this LED through this high value resistor. So as soon as this is on, you immediately see there's voltage in the circuit. So you want to be careful that you don't touch anything, especially with the high voltage coming in. And then the main capacitor discharge path is through this switch over here, normally closed switch, which then the capacitor leakage is measured on the return side through this ammeter over here. And if you want to discharge the cap, you can move the switch to the other side, and then it will disconnect the supply from the cap itself, but it will connect this resistor across the cap, which will then discharge it fairly rapidly depending on how long you want to wait. Unfortunately at this time I don't have a toggle switch. I have a momentarily connection switch, which means I have to press it to keep it in the normally closed open position. I need to keep it pressed to discharge it. I'm going to change that at some point to make it a toggle switch, so I can leave it in this position when it's lying around and it's not being used, just to be safe. So right now I've got to make sure I discharge the cap fully before I let it go, and then the switch will return to this position where it's connected to this side of the supply. So the box is really here. I've shown schematically or physically how the components are placed. I have the jacks for the ammeter in the front over here, these two plus and minus, and the plus and minus on the supply go on the back side of this thing, and then the capacitors and resistors, the resistors are just mounted freestanding inside this box, and it's a fairly small box, so I don't need any circuit board, and that really helps because any time you place a circuit board or any kind of substrate, you're going to have leakage on that as well. So this is all air over here, so it's just ideal for that kind of thing. The duct itself, the capacitor, is measured using these wires that come out of these two holes in the front here, and it's got a couple of clip-ons that I can clip onto any capacitor I want. Discharge switch is right now I mentioned is a press button, kind of a push button switch. So once I replace it with a toggle switch, it will be sitting at the back, so I don't have to use it unless I turning on and off the instrument is mostly done using this switch. So that's this whole thing, fairly simple as you can see. One more thing I wanted to mention, if you have a very low current this leakage, you can place a voltmeter over here. Once you charge the cap using a short, you can short out this terminal here, allow this capacitor to build up full charge, and then you remove that short and then put a voltmeter here. You're going to measure the leakage through this capacitor on the return path. So it's not as perfect as an ammeter, because this ammeter is a low impedance connection, so it would charge and keep the leakage going even while it's charging. So whereas for a voltmeter here, you've got to first pre-charge the cap and then remove that shorting wire here, and then connect the voltmeter across this 1 megohm resistor. So you could measure millivolts, and then you will measure nanoamps of leakage current here. So here's the jig that I built, fairly compact. This came out of a old 12 volt to 110 volt inverter, and that circuit didn't work, so I decided to use the box for this thing. So here are the front ammeter connections, plus and minus. At the back here are the high voltage or any voltage you want to apply through these two jacks. They come in, as you can see, from the positive into the switch, main switch, and then the other side of the switch goes to this LED resistor and the LED over here, and the return path for the LED is to ground over here, and then the positive of this also goes to that toggle switch or momentary push button switch, which I currently have over here. The output is then this, which goes to the capacitor, which is over here, which is through these leads, and the return black lead comes into the ammeter terminal, and then also the discharge resistors are here, which again shorts out the capacitor between this and this, and then the 1 mega ohm resistor across the ammeter terminals are here in case you want to use as a voltmeter measurement. So everything is very small. All the leads are, all the components are floating, fairly secure, so nothing is going to fall off or have any leakage from other sources. So I think this is perfect for a very low leakage measurement. And once I close the box, it's going to have also a fair amount of shielding from external sources. So let's now show you the setup and do some measurements. Before I go into some of the measurements, I just wanted to show you the connectors that I put on the jig, and I wanted to make sure that there was no chance that any of these terminals would touch the chassis, because it's all metal, and I had to drill holes through them, and there's a good chance it could shift slightly and touch, and you don't want a 500 volt touching the chassis while you're handling it. So notice the heat shrink tubing that I put on the two threads over there, and that should basically keep that central post clear of the metal chassis around it. And finally, this is what the two of those uh, pairs of jacks look like. The one at the back, of course, is a high voltage. The one at the front is basically not handling any significant amount of voltage there, just close to ground. So I think we are okay on that. So hopefully this setup is easy to see. Right now I have two ammeters here. This is actually an electrometer which can be used in ammeter mode, as well as voltmeter and ohms and so on. And here is my trusty multimeter, which can measure down to microamps. So currently the capacitor is a very high voltage electrolytic. It's a 1000 microfarad 300 volts, an excellent low leakage capacitor used in high voltage inverter type of equipment, and it's in good condition, so we can measure that. Here's my high voltage supply, which is the Bertan 210, which I had made a video earlier about repairing it. And so this one is also functional at the moment, so that's good. So I'm going to not use this for the moment. I'm going to do an electrolytic which has got fairly reasonable leakage, which even this meter can measure. So I'm going to power up carefully. So right now this meter is off. Of course this is safety is normally open, so it's only going to charge the cap. It's not going to discharge it or anything, so this doesn't do anything as such for now. And then I need to of course connect the high voltage supply. That will be good right here, and I have to make sure I don't touch there when it's turned on. So let's turn on the high voltage supply. So it's on. It's still set at 0. I'm going to turn on this switch. So it's got a slight glow there because I think there's some residual voltage on that particular capacitor. The only downside is with this switch, I don't have the toggle capability. I cannot leave it in the discharge position, which means that it's now not being discharged. Even though it's powered off, it still can maintain voltage. That's something I don't like, so I need to change that. So I'm going to raise the voltage here. So it's about 100 volts here, and you can see that the LED is brightly glowing at this point, and I have a leakage current of about, it's charging, so it's not the leakage really, it's actually the slow charging, the tail end of the charging. So that will take a while actually to settle down to some fairly steady value, so it's still going down. So what I'm going to do is to come back after a few minutes and then see where it is. So it's been a little over a minute, and you can see it's still falling slightly, but it's I think in the order of 10 microamps, 11 microamps, and voltage is 100 volts. So we'll do some calculations later to see if that makes sense for these type of caps. And typical leakages for electrolytics is based on some general empirical formula of multiplying the capacity or microfarads times the voltage capability and some fudge factors in there, so that depends on the manufacturer as well. So we'll look into that a little bit later, but for now it's still dropping. It's still a very good leakage for a large size capacitor, high voltage capacitor, electrolytic. So I'm going to increase it to 200 volts. So we were down to about 8 microamps. So right now it's exactly 200. And it's now again going to charge up and then discharge. Hopefully it will show about twice the leakage, but remains to be seen. It's still falling. So we'll come back in a minute. So as you can see, it's in the 20 microamp region, which is about twice of what I had seen earlier at 100 volts. So I think it's fairly linear in that sense, and I'm pretty happy that that is true. It's not too non-linear. As it increases the voltage, the thing's starting to breaking down and so on. So I think one thing I forgot to mention is that normally I wouldn't leave this open like this. These are high voltages. One has to be very careful dealing with these type of high voltage caps, and when you discharge them, you've got to make sure that they are fully discharged before touching them. So in this case, I'm going to carefully discharge this thing, going to the other side, and show you what happens. So right now the supply is connected, so the light is still on. That's one safety feature here. So if I turn off the supply here, turn it off here, now if I press this discharge switch, that light goes out because the external supply is now off. And right now the meter is also not active because I'm bypassing the meter when I'm shorting out that capacitor. You can see there's still a small amount of glow on that LED, so there's still about 30-40 volts left on it. If I keep doing it, it will actually fully extinguish, but like I mentioned, I would ideally have a switch here. I don't want to keep it pressed like this. So anyway, I think it's safe enough to handle right now. It's in the order of 10-20 volts there on that capacitor. So next I'm going to use a different type of cap, and then we'll use the other meter to measure a couple of caps. Okay, so now I'm going to use this meter, the electrometer, the Keithley, which has got a low current scale, and then I'm going to measure two caps similar value. This is a 220 nanofarad polyester, I believe, which has got no voltage rating, and this is the electrolytic 50 volts, also 220 nanofarad, 0.22 microfarad. I'm going to do this first and then use this meter, as I said. And so let's get started with this. Connect positive to the positive for the electrolytic and power on. So let's try this. Meter is on. So as you can see, the current is now in the microamps. and falling. So it's pretty stable already fairly quickly because it's a small capacitor. It's not going to take very long to charge up. It's, okay, this is now dropping. So leakage is now down to 170, 160 nanoamps. So it's not changing too quickly now, so I think we can assume it's in this neighborhood of about 150 to 160 nanoamps for the electrolytic cap, 0.22 microfarad, 50 volt rating. Next I'm going to do this other one here. Procedure to turn it off is again turn off this supply, and then it's already discharged because it's such a small cap. It's not able to even, I don't need to do an extra discharge cycle here. So that's the good thing about these very small caps, they discharge pretty quickly. I still have 40 volts there. I'm going to bring it back down to 0. Connect this 0.22 microfarad. And raise this back to 40 volts. As you can see, the leakage is much smaller this time. One point, it's a bit noisy at this point, but I would say it's in the 1 nanoamp realm. That would be the leakage for this thing. So it's about 170 times, 150 times less leakage than the electrolytic version. So that's the good thing about these electrometers, which have very, very low current measuring capabilities. But you also have to deal with noise, as you can see at these low current values. So again, if I turn this off, it pretty quickly discharges itself because of that. LED circuit itself is enough to quickly discharge it out. So here's another small cap. This is slightly about 10 times, 20 times larger. This is a 4.7 microfarad, 50 volts again. And we'll see if it tracks the higher leakage being a larger value cap with same voltage rating. I'm going to switch it on again. I'm going to bring it back down to 0 here. Turn it on. There was some charge already there briefly. I'm going to raise this to 40 volts again. So it is taking a bit longer to charge up, as you can see, but it's now quickly falling to under 1 microamp. And based on the previous measurement of a 0.22 microfarad, this is 20 times larger, so expect leakage to be correspondingly higher for the same quality of the cap. So let's see where this ends up. So a minute later or so, and you can see it's a little bit larger leakage and it's fairly stable at this point, 0.26 0.27 nanoamps, say microamps, which is 260 or 250 nanoamperes. So if you recall, we did this capacitor which had about a nanoampere of leakage. Now I'm going to measure the voltage and see the voltage method. So for that, I'm going to switch this to voltage. It's almost fully charged now, so go to volts, and of course it's going to read similar in now millivolts. So if I short this out, now I'm fully charged the cap, and then I'm going to remove this one. and you'll see that it's a similar level, 1 millivolt or so. It's quite noisy and it's not as good as the current reading, but it gives you similar values, about a millivolt or so, which translate back to a nanoamp, because it's a 1 megaohm resistor across that ampere ammeter terminals. So this is another way of measuring the same thing using voltage. So this video barely scratched the surface of capacitor leakage testing. I demoed electrolytic cap, and then some smaller caps, electrolytic and polyester cap, to show the typical level of leakage that you can expect. And the graphs over here kind of indicate a little bit more detail about how this leakage is affected by, uh, first of all, by the time you allow it to uh, settle down. Typically, if you don't test it for at least 30 minutes or an hour, you're not going to see the true leakage. As you can see from the first graph, I was barely testing it for a few minutes, so I'm probably seeing 3 to 4 times the leakage of what the cap would really have long term. The second graph tells you the temperature effects. Fortunately, here we are operating close to room temperature, around 20 to 30 degrees Celsius, so we're probably okay in there. The leakage is around 1 for that, so that's fairly realistic. And on the third one, I wasn't testing really at the rated voltage for the cap. I was probably halfway there, maybe two-thirds way there, at least for some of the high voltage testing. But so I was probably seeing about 70% of the leakage or 50% of leakage. To really see the full leakage, you have to go to the rated value, and if you go a little bit above that, it starts to very quickly increase. So a bad cap, of course, would start taking off vertically in the leakage on this third graph if it's bad. So you don't want to stress it and probably blow it up. So I think that's probably a more careful test you have to do when you're evaluating unknown cap. So to conclude this video, I'm going to go over the leakage formulas that many manufacturers are using in their data sheets. So the main thing we want to look at is the leakage, that is I leak, and that's usually specified in microamps. Typically the measurement is done after 2 minutes or 5 minutes, or some cases even 10 minutes, and different manufacturers have different times that they specify. The third, of course, important thing is the capacitance of the device you're trying to measure. It's the rated capacitance in microfarads again. And the lastly, we need to know the rated voltage or the maximum rated voltage in volts. So different formulas are there. The first one is the most common one I've seen from different manufacturers like Vishay and Worth and so on. And that's just simply 0.01 times C times V. Minimum of that. That's a minimum. Sorry, that's a maximum value that's supposed to be present as leakage. The other formulas like 0.01 C times V or 3, whichever is the larger one, or this these are for low voltage and larger capacitance value caps. And there's another one which is 0.06 times C times V plus 10. This is a plus 10, not or 10. And again, this is from Panasonic and Chemet. These are for a little bit for higher voltage and smaller capacitance value caps. And lastly, there's one from TDK EPCOS, which is specified as less than 0.02 times C over microfarad, which that means 10 to the minus 6 times VR divided by V, and whole thing is raised to the power of 0.85 plus 4 microamps. Somehow I think this is an error in this formula. It should be, I thought it should be V over VR, because as you, if your voltage, if you test it at a lower voltage compared to its rating, you're going to see less leakage, whereas this formula indicates a higher leakage. So I'm not so sure. Of course, these are for electrolytic caps, and they tend to have these type of formulas. But for Other types of caps, I haven't come across anything. They tend to be extremely low leakage anyway, and we talk more about insulation resistance rather than leakage for those type of caps, which may be in the nanoamps or even lower leakage values. So I was particularly interested in measuring leakage at very low levels because of some applications I was thinking of using these caps for, such as using low voltage, low current charging, and so on, to measure its effect on the voltage that would be generated and stored on a cap. If you have a high leakage in the realm of microamps, it's not going to be very useful. So I was looking at extremely low leakage caps for that. So that's my interest in this whole thing. So here we are at the end of this video, and it's time to summarize. One aspect of capacitor testing is leakage, and this video focused mostly on that. Uh, the other aspects, of course, are to measure the capacitance, which is important, of course, and the ESR. Uh, the capacitance measurement, of course, is fairly trivial these days, but the ESR could be a little bit challenging, and I've done a video on this before. Low leakage indicates high quality capacitor, and it affects lifetime and long-term reliability of the capacitor and eventually the system that this capacitor is sitting in. So you wanted to make sure that a capacitor doesn't blow up or short something or cause some problems that damages an expensive piece of equipment and also does the job it's supposed to do. In this video, we built a jig to test a leakage of a capacitor using external supplies and meters. Uh, it was quick and it's an accurate setup without too much of an investment. That is, if you have existing equipment like meters and power supplies, it's actually quite easy to build up something that works for you in terms of the specifications you want to test for. It might be overkill in a lot of respects because I was using some of the equipment was fairly expensive in terms of like the electrometer, or if you have a even more expensive digital electrometer, of course it can measure extremely low currents, but you probably don't need it for electrolytic cap testing. So my application was a little bit more broad in that sense that I could use it for measuring leakage of other types of lower valued capacitors, non-electrolytics, and so on. So we demoed the setup for both high and low voltages. I didn't do too much of a measurement. I just built this thing a few days ago and I'm just trying it out. So whatever I did was just to illustrate that it's actually doing its job. I think there's a lot more to be learned about testing of leakage, how you measure it, how long you measure it for, and what kind of voltages you apply, and the safety factors that need to be considered. And finally, discuss the typical formulas that are used in electrolytic cap uh, currents that are leakage currents that are given in data sheets. So different manufacturers have different formulas, and which probably play to their strengths in how they give those formulas. But for us, these are just starting points, and with this kind of a setup, you can confirm that these capacitors are meeting their specifications, and they are also safe to use in a given application. So hopefully this video was useful, a bit of a long video, but it's definitely useful to me, and I learned a few things from doing this thing. So see you next time. Bye.